here for the PhD defense of Mr. Kaushik Roy, who is present online. The members of the committee are the major professor and advisor Amit Sheth, Vignesh Narayanan, Amitabh Das, and Alessandro Tamari, who is the external committee member. I'm Marco Valtorta, the chair of the examining committee, and I'm the only one present in person at the AI Institute today. The audience, the 10 people here, mainly students. So let's get started. Mr. Roy, we will ask questions detail as you do the presentation and have the bigger questions for the end. Let us proceed like that as usual. I imagine you have some slides prepared for us. So are you going to share them? Is that what is happening? Okay, great. Let's start then. Let's roll.
Yes.
Are the slides visible?
Yes.
Yeah. Yes. Okay. So good morning, everyone. This is my PhD defense presentation on process-grounded neurosymbolic AI. My committee members are Dr. Sheth, my advisor, Dr. Marco Valtorta, the chair and the graduate director, Dr. Vignesh Narayanan, a close collaborator and assistant professor at the school, Dr. Alessandro Ultramari, my internship mentor, manager, and for a couple of internships, and he's at Bosch, senior research scientist at Bosch and president at Carnegie Bosch Institute. And Dr. Amitabh Das, my fiercest critic at Birla Institute of Technology right now and in Goa, India. Okay.
A quick point. Dr. Narayanan has showed up in person too, so there are two of us in the room. Thank you.
Yeah, and Kaushik, if you can just turn your thing so that light is not behind, shining on behind you. Just
Let me see.
yeah, or block the light.
Yeah. Let me see.
Okay.
Okay, so this is the outline. First, I'll be motivating the topic with a sort of simulated example and then with an example that actually happens in real life. I'll introduce the defense statement and then I'll get into the details in part 2 of what are the problem specifics, objective impact, formulation, etc. And in part 3, I'll get into the nitty-gritties, which would be the details of the method. Not all the mathematical details, but at least conceptually. And feel free to ask questions in between. In part 4, we'll be contrasting my work against prior work and how, when you zoom out, where does it land in the landscape of AI today? And then open challenges will be part 5. Okay, so we'll begin with part 1. So imagine you want an ice cream that is vegan and you want it from a shop that is 30 minutes within the vicinity. So if you give this query off to the most sophisticated agent-based architecture today, which is called Autogen by Microsoft, what it will do is seemingly sensible things like map the locality, obtain the relevant information, filter by constraints, which is vegan in this case, consolidate all the information and bring it back. But then you might find, and this has happened with me, that you go there and the establishment is closed because it's holiday hours or for some other reason. So those kinds of sanity checks or robust things that people would do without asking, the agent seems to miss, right? So this is a sort of
Kaushik, you're
You
breaking.
you're breaking very badly.
You would need to it's always easier to
Kaushik, we can't hear you.
So you might need to walk me. Do you see the slide?
Yeah.
Okay. So where did it get blocked in this slide?
Yeah.
Okay. So I'll start
And
with
we were
the
talking about ice cream.
okay. So
Vegan
so
ice cream.
let's imagine that we were ordering vegan ice cream within 30 minutes of us. If you give this problem off to a sophisticated agent-based AI today system, then it does seemingly sensible things like map the locality, obtain the relevant information, filter by constraints, which is vegan options in this case, and then consolidate that information. It seems to make sense at first glance, but it doesn't do any things that a human might do without asking. For example, check if the place is even open. What are the hours? Is it holiday hours? Is it closed? So you go there and you find the establishment closed after all that. So that would be a problem. So this is a kind of motivation for why it's better to bootstrap these systems with knowledge of processes. I'll get more formal about that in a minute. Before you let them do their thing. So where does this manifest in real life? Even though in the going back to the simulated case, I intended for this to be a sort of toy example. Even here, you could imagine there being ramifications that are extremely suboptimal. For instance, if the agent actually provided them the vegan option and didn't check for allergies or something like that. So in the kind of work that I do, the way that this manifests is if you're trying to diagnose a patient, you make use of information that a doctor would actually use, which is go through a diagnostic checklist, the PHQ-9 in this case for depression diagnosis, a checklist of 9 questions. You then, based on the tally of final scores, make a treatment recommendation. And then in doing so, in carrying out those 2 intermediate steps, you can then explain to the patient or the provider that this is why their treatment recommendation is so and so. This is the process that you would follow for depression diagnosis in real life. And if you are asking an AI system to assist with this process, you would like it to follow a similar process versus just suddenly predicting a recommendation. So this is then the defense statement. Infusing process knowledge into AI systems is crucial. By grounding learning and reasoning in expert-defined process structures, we'll achieve high accuracy, but also dramatically improve explainability and safety. So that brings me to the end of part 1. Part 2 is, so what actually is the problem in current AI systems? AI systems are the most popular ones today. That's not the all of AI, but neural networks and their different flavors are black boxes. They lack explainability and control. So it's not easy to get them to modify their behaviors in any controllable manner. So this becomes an issue, especially in high-stakes tasks like medical diagnosis. And our objective is then to integrate those control knobs in the form of domain expertise and process knowledge into learning and reasoning outcomes and process methods, so that we can ensure not only accuracy, which actually black box neural networks do pretty good at, but more importantly, explainability and safety in the outputs. The impact of this is not just confined to the medical domain. You can substitute any high stakes application here, as we have done, as I'll come to later. And it has the potential for improving AI systems to build on their already significant accuracy and at the same time bolster their explainability and safety. So okay, so that's the problem statement, objective, and the impact. So what's the core methodology? Core methodology is that we'll need a representation for the process. We'll need an integration mechanism with the neural network and the process. This is non-trivial because the process is going to have a symbolic representation, and neural networks don't play nice with symbolic representation. Safety and explainability is going to be an outcome. When the output is produced by such an integrated system, the expectation is that it will be aligned with expert guidelines and provide safe and explainable outputs. Flexibility, meaning it will support all manner of complexity in process infusion. Linear processes like the checklist that you saw, and non-linear processes that we'll see in a minute. So some formulation, let's call the input X, the output Y. The process knowledge consists of a set of conditions C1 to Cn, and each Ci, for simplicity in my work, takes 0 or 1 values. It can take any number of discrete values. A mapping function that maps the input, for example, how do you know that a patient satisfies a particular condition? So that mapping function tells you information like that. A decision function that once you have mapped it to the criteria in the process knowledge, then what's the treatment recommendation, for instance, or what's the diagnosis? So that's the decision function. You can compose decision functions. For instance, you can first diagnose and then treat, recommend a treatment. So the decision function can be compositional. So key scenarios that I'll cover in this presentation is categorical decision making, whether a person is depressed or not depressed based on diagnostic criteria. Natural language explanation generation, which is a composition on top of the decision, further explaining the decision. And multi-stage processes, which is compositional categorical decision making, first diagnosis and then treatment recommendation as a prediction. So getting into the core methods. Here is an example illustration using the notation I just described, staying with the example that I introduced earlier. The input X is the patient data. C is the checklist, diagnostic checklist, 1 to 9 questions. Embedding EX is how do you represent the patient data? You pass it through some text-based model, and then you get numerical values as a list. That's called an embedding. And then you take those set of numerical values and you pass it to a mapping function, and it tells you which conditions are satisfied. Similarly, you can then pass the outputs of that mapping function to the decision function, and it can tell you if the diagnosis is one way or the other. And you can pass the mapping function outputs to a text generator, which can explain to you in verbose form why the mapping is one way or the other. I mean, why the decision is one way or the other. So we'll see some examples of that. These are the publications in which these methods are explained and demonstrated. So first, the diagnosis. You start with the embedding of the patient data. A neural network maps the patient data to the conditions on the checklist. The decision function is compositional in deciding, once the mapping is determined, then what's the function of that mapping that leads to the final decision. Is this person depressed or not? It looks maybe a little complicated at first glance, but it's because this is a linear checklist, it's just a sum, and then it's a weighted sum. If that weighted sum crosses a particular threshold, then you squash it, and you squash it to a number between 0 and 1 that finally tells you if it's a false case or a true case. The explanation generation part is you take the representation before squashing it, and then you pass it to a text generator model that is trained to produce natural language explanations from such representations, and you get the explanation. The recommendation is similar process, but instead of text generation, you get treatment recommendation that you see in the third column. Feel free to stop me at any time. So the method that I showed you is the method that is described in the paper. The reason it's novel is because this you can see is a multi-stage sort of rule-based looking process. But when you compose it this way, I sort of brushed under the carpet that you take the 9 checklist items and you can represent it as a summation. That's the tricky part, that how do you take discrete operations and then make them continuous so that you can differentiate through them later, because learning depends on differentiability. So those are the novel bits. How do you take these decision checklists or flowcharts and then turn them into a structure that you can differentiate through?
Kaushik, this is Michael Humes. If I can interrupt at this point, my question might be slightly orthogonal to your process or your objectives, but the process, like the ice cream process, there are 3 steps to it. Those steps can be taken in different orders. And so you could first find vegan places, then see if they have ice cream, then see if they're near you. Or you could first find everything that's near you and then see which ones are vegan and which ones have ice cream. So the ordering of the process can drastically affect the efficiency of the outcome. And
right.
So, and I noticed that you have a vector C, and it seems that those steps in that vector, either being 0 or 1, are ordered temporally from C0 to C whatever. And so that temporal ordering, which is the ordering of the steps in the process, is that reasoned about at all? Is that any part of the explanation that you propose to generate? Or is that sort of a given before any of this, any of your work begins?
That's a great question. So here, the C1 to CM, this is a set. So there's no temporality implied here. C1 to CM are the conditions that would be placed in some temporal order, and that order would be given by the process knowledge itself, by the domain expert. For instance, in the PHQ-9, they have these 9 questions in order that you're supposed to ask. In a different flowchart, like let's say suicidality, you have conditionals that you have to evaluate at various points, go left or right, but the temporality is implied from top to bottom. After that, it's up to the neural network to figure out if there is some implicit temporality involved. I haven't explicitly dealt with that case beyond encoding it explicitly in the knowledge.
Thank you. That's a good explanation. And I know sort of analogously to query processing in databases, the order of the steps is the order that you might do a join, and those can have vastly different time results based on how you order that. And so that's similar to this process that you've been describing. So anyhow, thank you. That's a nice explanation.
Thank you. So I'll now cover the baseline. So what was the state of the art at the time? The first one is BERT-based. For those who don't know, BERT is expanded as bidirectional encoder model. So that's autoregressive transformer, so BERT. What that is it's a text predictor. So given a partial text, what's the next word? Predict that word. And it's bidirectional because the context encoding is bidirectional. So for instance, if you're predicting I used to be all about painting, I mean, you give the input I used to be all about, and you want to predict what's next. About, the word about would have the context from I used to be all, and it would also have forward context from painting. I should have chosen all. Let's choose the word all. All would have, because painting is the word we are predicting, it's masked, so painting doesn't exist anymore. But all would have bidirectional context, context from the words before and the context from the words after. So that's the way BERT operates. Other than that, it's a transformer. Transformer has its nitty-gritties that I won't go into unless you want to know. This is a BERT-based baseline. What you can do with a BERT-based baseline is you can take the penultimate layer of the neural network, and you can pass it through some visualization mechanisms. For example, you could sum over all the gradients with respect to the output. That's called integrated gradients. And you can get a strength of which words contribute more to the output. And you can highlight them. Okay, so if we did that, then what you would find is that the highlights seemingly don't correspond at all to the accepted definition of depression, which you see in this box here. But the prediction that this person is depressed is 0.99. So what's going on here? The answer to that, what's going on here, is impossible to determine nearly, because this is entirely black box. The integrated gradients tell you some highlights. You could repeat these experiments, collect all the highlights, try and figure out some pattern. But that would be extremely tedious and still not guaranteed to be indicative of the internal mechanisms of the network. So that's baseline one. Baseline two is the more powerful ones, the GPTs. So you take at that time, I think it was 3.5. You can take a Text DaVinci and do the same highlight trick, but you can take ChatGPT 3.5 and then you can ask it to explain why is this person depressed. And still you see that while the explanation may be sensible, it does nothing for a provider. A provider has to go by the textbook. So which part of the textbook definition matters here? It's not clear. So when you're talking about AI assistants for a provider, if they have to do so much heavy lifting, then these kinds of techniques, sophisticated as they are, fall extremely short. So then what was the method that I employed to try to address that challenge? So as I alluded to earlier, you take the process knowledge and you construct a differentiable relaxation of it, right? And then what you can do is the same thing that you did with BERT and GPT. Take that differentiable relaxation, visualize its penultimate layer. For instance, that differential relaxation can be a neural network. Then you find its similarity to one of the actual criteria in the process knowledge. So then what happens is when you do that trick, you find similarity to subdefinition A. You find similarity to subdefinition B, for instance. And that is what the network is trained to do, because you train it across a whole training data set with that explicit formulation. So it is trained to only try to find similarity between the input text and the process criteria, nothing else, right? So that's all you want. And for the corner cases, you can still use a neural network. So that's method number one. In this case, you see that for the expert, they get highlights that are pertinent to them. They get a score that makes sense. It's not 0.99 anymore. They get a score that actually matches the tallies that they conduct. And so now they immediately have something to work with. If they have questions or they're unsatisfied with the output or they think it's suboptimal, then we can do something about it. But so in the paper that we wrote on this, the satisfaction rate was up to about 80%. The dissatisfaction was mostly around false positives. So you had data from gamers who would use explicit language, and it will classify them as depressed. They were not depressed. So that kind of thing. This is same method, but applied to a nonlinear structure. Like I mentioned earlier, this is for suicidality. You go through this series of questions, but there are conditionals to be evaluated at various intermediate stages. In this case, the agreement was about 70% versus 80% in the depression case, but the best baseline neural network at the time, TextDaVinci, got up to 47% satisfaction with experts. Okay, so now we'll move to text generation. In text generation, there's only one modification, which is that instead of predicting a labeled output, you predict a sentence. So that's significantly harder to stabilize at training time. So we had to experiment a lot with which architecture should be used, and in the end, we ended up using an LSTM. We couldn't get a transformer to stabilize. So the output was pretty good. You compare it against GPT-2 at the time, because we couldn't get GPT 3.5 on our laptops at the time. So you see that GPT-2 produces maybe reasonable responses, but the expert didn't like them because they're sort of triggering to the person having the conversation. And what the expert did for us is give some example questions, a lexicon of things they definitely wouldn't use. And when we incorporate all that, you get more tame responses. Method is similar to what I've already described. Take all of the symbolic information that they've given, construct a differentiable relaxation, plug in your favorite neural network, in this case an LSTM, or what works, hyperparameter tuning based, and then you test it out on inference time. Okay, so these are the numbers. These are the publications for those methods. There's also a demo where you tie up everything together, so both diagnosis and text generation. Okay, so in the last one, up until that point, we were not in the large language model era. Now we are in the large language model era, so we can get into the really good model, GPT 3.5 onwards. So in the core method in 3, which is just got accepted to ACM transactions in healthcare, we did the same thing, but with models like Llama 3 and all those more advanced models. The results on that are very good. They've gone up to, in terms of accuracy points, up to 90% plus, but the expert evaluation on that is still pending. This is an illustration of the demo, what it does. There's a patient view where the patient is talking to the chatbot. There's a clinician view where you have how is that chatbot conversation being transformed into a knowledge graph, and then how are conditions being applied, the process conditions, and so on. And then what's the hypothesis generated by the AI assistant. Okay. So here is an illustration of how you might obtain explanations beyond connections to the definition. You can also obtain connections to concepts that are in their textbooks. You can do that with the same kind of similarity matching once you have trained it for such similarity. So okay, so yeah, so this is really informative to a provider because you get a class hierarchy of everything that's going on instead of just a label on what's going on. much more information for them to work with. Not only do you get a conceptual class hierarchy, but it also connects nicely to the definition, as we already saw, the definition being this top right corner. So the takeaway from this slide would be, up until this point, for instance, in my seniors like Manas, in their dissertation, they showed how to integrate neural networks to identify concepts, like you see on the left-hand side. The thing that I've added is how do you connect to definition and processes. So you put both of that together and you get a really robust output. Okay, so yeah, like I mentioned, the current results are between 87 and 94% in accuracy. And this is the result summary. Up until this point, I'd done all my work in the mental health domain. From here on out, I'm trying to explain how to maybe generalize it so that it can be applied to other domains. This is a proof of concept that the method works in a high stakes application.
Mr. Roy, a quick question. Going back 2 slides, what do you mean by conceptual flow? How do you measure it?
That's a good question. So there's a model called Roberta NNLI, stands for Natural Language Inference, and it has classes. The class labels are entailment, contradiction, or neutral. And so the input to that model is a pair of sentences, and the output is one of those 3 labels. And if those 3 labels are consistently entailed, then you have coherence in the conversation or in the sequence of text. That's the assumption. They've been trained to measure entailment or coherence in a particular passage.
Thank you.
So generalization is what I'm calling systematization. So how might we do that? So we see that there's a symbolic component, we see that there's a neural component. So the most obvious candidate would be to survey neurosymbolic approaches. But beyond that, during my internships, I was exposed to other kinds of AI system architectures, like cognitive architectures. So we did some exploring on that front. And finally, in classical AI, people have done a lot of work in integrating symbolic planning and sub-symbolic systems. And more recently, that has translated to efforts to integrate symbolic planning and language models. So we also surveyed that. Starting with neurosymbolic AI, this is a paper we wrote in 2023. It has 2 categorizations. One is where you try to take the symbolic structure and you compress it into a vector space so that you can integrate it, preferably the same vector space that the neural network operates in. The second method would be you take the neural network, you take the objects in its vector space, and you try to interpret them in a way that they turn into symbolic information. For instance, you could interpret objects in the vector space as a graph, and then work with that. In the first method, there are a few subcategories of state-of-the-art methods. And the algorithm level features that we'd like to see is large-scale perception. In this case, scale means that it can scale to large data sets. So large-scale perception, meaning if you have a lot of text, can you compress all that text into vector space quickly? Abstraction, meaning does the vector space capture concepts at hierarchical levels? Analogy, does the vector space know that one kind of diagnosis is analogous to a second kind of diagnosis in terms of the process followed sometimes? For instance, there are commonalities in a certain diagnostic criteria across mental illnesses. And planning meaning sequential decision making. Application level features, these are important to the end user. Does the system, the explanation that the system provides for its outputs is that anything that they can work with or scrutinize. Domain constraints. The sanity checks that they would perform, does the system perform those sanity checks? Scalability in this case, it means that is it usable in real world settings with high volume of individual users? Continual, so the system is bound to make mistakes when it's working with a human operator, so then can you modify it quickly enough? You can modify it by taking it offline and then redoing the whole process, but continual in this case implies modifying it sort of on the go. So those are the application features desired. So I'll not get into this very much, except for I'll touch on 2A, which is now evolved into agentic systems. Since the advent of language models, what happened at the time of writing this paper is what was known then as federated pipeline methods. You take a query, you use a second language model to interpret the functions in that query. For instance, is there a math operation involved? Is there a search operation involved? In that case, siphon off the math operation to Wolfram's calculator, the search operation to Google SERP API, and so on. When people started getting very fancy with it, evolved into agentic architectures. So today, the state of the art is considered 2A and how it's implemented using various toolkits available today. The place where we would want to get to is 2B, which is the sort of thing I explained with the mental health example so far. End-to-end differentiable, but process infused, knowledge infused, both declarative and procedural. Cognitive architecture. So in cognitive architectures, you have all these components. There's a perception cognition cycle. You start with perception, and then you have various memory structures to help you with long-term storage, process storage procedures, and working memory. It's like a running scratchpad. At execution time, how much should you pull from the procedure on long-term memory when executing? The action part is, I haven't worked with a lot. For instance, if this was a robot, the action would involve the motor and things like that. So this is a cognitive architecture. A cognitive architecture really appeals to me because it models the human brain. It has a rich theory, well-established theory, a lot of proven literature. So, and most importantly, people that have developed cognitive architectures, they have paid a very good amount of attention to the software readiness of these implementations. So that's why this appealed to me. In integration of planning and language models, you have all these categories. Language translation. This is maybe the simpler case where you have to go from one syntax to another. Plan generation, this is a really hard problem. Model construction. So model construction is the AI system needs to have a model of the task before it can plan meaningfully. So that model needs to only contain things that are within scope. So things that are relevant to the actions in the plan, and that's very hard to do. Right? So an LLM a language model can be useful for defining some of that. And then you have multi-agent planning, which is the classic agentic system today that uses LLM and does executes on a query by spawning multiple agents, executing processes, consolidating the output, and bringing it back. Interactive planning. So the agent today, if you use a software like AutoGen that I showed on the first slide, sometimes it asks you questions that, are you sure this is what you want? So, or can you clarify this particular aspect of your query? So that's interactive planning. Heuristic optimization. If you let the agentic system today just do whatever it wants to find you the answer, you'll probably find a very large bill. So you want to optimize for the number of steps and other heuristics like that. Tool integration. So like I mentioned earlier, sometimes you need math, sometimes you need search, sometimes you need calendar booking. So tool integration allows you to do all of them. Brain-inspired planning. So in brain-inspired planning, you use literature available about what people understand about our brain and try and encode that into agentic planners. The study that I've conducted across those categories are in these publications. They're mostly conceptual in nature. I have executed on some of it. Okay, so let's look at prior work. Workflow modeling has been around for a long time. So in the in AI systems, we had classical planning. We talked a good bit about that, but we had workflow engines, business process management language, flowcharts, rule-based orchestration. They're pretty rigid. You used to model the process completely explicitly, including the exceptions. And the exception list usually was bigger than the actual process itself. Then in more machine learning times, you had decision trees, association mining, process mining, and hierarchical reinforcement learning. They had their advantages and disadvantages, but when you look left to right across all of them, no general trend emerged. And also the end-to-end differentiability that I've tried to emphasize in my work, that was not there. People did not understand clearly how to integrate symbolic and neural networks in a seamless manner. In my work, I've made concrete steps towards that. There's still a lot to be done, but it has shown extremely promising results, and we're building on that. So prior work I'm going to cover from 4 different perspectives. Sorry, is there a question? Okay. This was on how were processes modeled. This is on how do you do the multiple steps of reasoning versus a single step of reasoning. So today, for instance, people will be familiar with chain of thought and different kinds of thought-based prompting methods. That's the current standard for multi-step decision making. In prior work, scholars have thought a lot about this problem, Daniel Kahneman being the most famous one, I think, in his thinking fast and slow conceptualization. So deep learning as an end-to-end architecture does not lend itself to a clean interpretation in terms of what are its multiple steps of thinking. So between Kahneman's work and more classical works, the chain of thought, there wasn't much progress. But today with LLMs, there seems to be several promising thought-based methods. Still, the problem remains.
Roy, there is a question. There's a question from Dr. Shen.
Yes.
Yes, Kaushik, while chain of thought is state of the art in the language model context in the current set of techniques, that doesn't does it imply that it has the control of both data and process flow or that we had in the earlier effort? And so if you think about it, the workflows that we used to implement, workflows or process, was fairly controlled. And there was a lot of context because there were schemas, there were understanding of what object from one step to another step moves forward.
Mm-hmm.
Here in chain of thought, everything is happening under the black box.
Yeah.
And furthermore, it has very powerful statistical model, probabilistic model of the data, but it does not have any ability to control, as you have done in specification of process knowledge.
Mm-hmm.
How do you provide the specific process knowledge as in medical guideline and control the chain of thought? Can they do that? Because even if you try to do that, and possibly you can do that in the sense that you can write the set of prompts at each of the at each of the steps and give guidance, but that guidance has to be translated from a very potentially highly accurate structure form into some language specification in natural language text. And
Right.
that could be a lot of things lost in translation.
Right. Absolutely. So the problem remains that I was going to say everything that Dr. Shad just said, that fundamentally the system is still black box. So it can say that it's doing step 1, 2, 3 in a particular manner, but then you have to just take it at its word at the end of the day. You can evaluate it to see if it's correct or not. But that's very hard to do because like Dr. Shah just mentioned, that there are multiple correct answers to a question. So just evaluating the answer is not enough. The steps are the most important part, the actual process. I've shown you repeatedly that the model neural networks, they produce 0.99 predictions and highlight things that don't correspond to the definitions at all. So there's no reason to expect that the activations in the internal mechanics of these larger, more powerful neural networks correspond to the outputs that they're actually producing. So that's a very concerning thing. So what do we do about that? So what we are trying to do about that today is encapsulated in the open challenge section. I'll come to that later. But for right now, it still is a matter of concern, for at least if you're deploying these things in use case scenarios like medical diagnosis.
Kaushik,
Yeah.
it's Alessandro. If I can add on that, I think what you have shown in your work, especially when you said when you described the theoretical foundational work on cognitive architecture and such, is that when it's not just about the symbolic descriptions you can map to a language model output, and it's not even about only looking at more structure symbolic representation like a chain of thought of similar let's say insights, let's call it this way. In fact, it's arguable that there is a mapping between the level of human symbolic representations and the machine level symbolic representations. There is work in the state of the art that shows that when we impose our symbolic structures that are well defined, compositional in nature and so on, we actually we should properly align those to very scattered semantic features in the neural networks. The work by Pradeep Ravikumar shows that, and I think you actually hinted at some of those results, if you want, or insights in your work. So I just also to highlight that here.
Thank you. Yeah. That there's multiple works that are converging. I think if I did a lot of digging, we would find that to show similar insights. These large language models, there's no denying they have been extremely useful for a lot of things, but their multiple works seem to be showing them converging to similar important concerning problems that have to be handled for any reasonable deployment of an AI system in the real world. So that's an exciting frontier, I think. So the third perspective on prior work will then be process formalization. Okay, so I talked about process representation, but then process formalization in this case means that, okay, you can have a representation like logic or knowledge graphs, but then you'll have to relax it a bit. For instance, strips is a relaxation of first order logic. The reason for such a relaxation would be the intractability of full first order logic. Similarly, in other cases, people have tried probabilistic relaxations. Hybrid ways to implement the logic, like neurosymbolic approaches, for instance, logic tensor networks and so on. What do you get by doing such relaxations? Mostly efficiency, computational efficiency, because symbolic representations in their full glory are definitely intractable. They're provably intractable. So you would need some kind of formalization added formalization to make them tractable computationally. And now when you start exploring choices to do that, which one's more flexible versus the other? Neural networks are, of course, the most flexible because they're proven universal approximators. But you can get a good amount of flexibility with probabilistic relaxation, more recently energy-based models and so on. What was presented in this work is a form of relaxation that doesn't depend on specifics like should you use a probabilistic relaxation or a neural relaxation. It has a general form that you take a symbolic input and you lay out the flowchart or decision structure in a differentiable form. After that mapping function you can choose dependent on requirements. It can be a neural network, can be a probability model, can be an energy-based model, and so on. So that's how this work improves on this effort. Integrating process knowledge into learning. So this has been pretty, how should I say, decoupled so far. You have neurosymbolic hybrid approaches where you first encode the rules of the game into the search tree, and then all of the heavy duty lifting and game playing and then reasoning about which is the right move set is done by the neural network after that. So it's decoupled. You could do them entirely separately and they would never, those two modules would never need to talk to each other. Similar case with the remaining papers presented here. Program synthesis takes the input and converts it into a program, like for instance, a functional program, and then the interpreter can execute that and give the output. So this decoupled manner, why is it flawed? It's flawed because like Dr. Shet mentioned earlier, the lost in translation part, you don't know if the translation is happening correctly, even if the symbolic interpreter then can execute with pristine accuracy the program. So in this dissertation, the learning is happening in an integrated fashion, end-to-end differentiable. So that's an important advance. Just putting it all together, all those perspectives. So you get ultimately better accuracy, scalability to large data sets, explainability, and safety. This is a snapshot of some of the more impactful works I've had. This is a landscape. This is a landscape of what are the core computer science related concepts and what are the application areas that I've applied my work to and where have they been published. So part 5, open challenges. Now,
Mr. Roy, I'm sorry, this is a bit of an off question, but can you go back one more slide? The list of references you have? Yeah, that one.
Yeah.
So the third one, that is unrelated to your dissertation, I assume. Is that correct?
That's unrelated. That's I used it to obtain some efficiency insights, but it's not entirely related conceptually. Yeah.
It's very interesting. Thank you.
Okay. So coming to the open challenges.
May I ask one question in this chapter? I mean, So in recent time, let's say in last 1 year, a lot of things change. In medical licensing exam in the US, typically the success rate of human is 60-70%. So both the model, let's say MedPalm-2, GPT-4 is above 85%.
Mhm.
So when you say that chain of thought does not work, is it a presumption or you have empirical proof? Did you try chain of thought at all and compare your results along with that?
For accuracy, it works. For accuracy,
Anyway,
all of them.
I know you started, your work at certain time, you end it up and etc. And my question also has a longer answer, but it's a, this is my, general question. But anyway, we'll come back probably later, little bit on
Okay.
this.
I have tried in that prompting guide every thought-based method. In the ACM transactions paper, the results is there. The accuracy is very high. Like I mentioned, it is above 90%. The explanation is still to be evaluated by the human expert. So
Yeah, even there is a report on that. Anyways, we'll come back.
okay. Okay. So the open challenge is I should I guess we're up to some. So the open challenge is today's AI systems, we need a lot of clarity in how they're working across all of these various 14 aspects. In this dissertation, we touched upon explainability and safety, but you need a lot more than that for a robust system. You need reliability every time you use the system. It can't be failing on corner cases. You can't keep adding corner cases. You need consistent outputs. You need alignment with the end user's expectations. That's what alignment means here. You need analogy. For instance, you don't want to do redundant computation every time. You want to be able to use structures that have applied before to make computation easier. Abstraction, it ties into analogy. Causality, yeah, the system has to be aware of what makes sense to do after what, temporally say in actions. Instructability, in the event that the system is not performing optimally, then the human should be able to say in plain language or in some easy translation that the system should be doing something different. Reasoning. Reasoning should be explicit. Chain of thought and all the various thoughts are constructing a thought pattern, but we don't know if their internal reasoning corresponds to that thought pattern at all. Planning is a similar case to reasoning, is sequential reasoning. Grounding is grounding in real world representations, a model of the real world rather. And then finally attribution. So can the model point to the things that it constructed its information from? So you can categorize several of those. These are not mutually exclusive sets, but into three broad categories: robust, trustworthy, and intelligent. And we are envisioning that these three are required for enterprise grade systems that you can actually deploy in the real world or in mission critical settings. There's a publication on this if you would like to read it. And finally, thank you to all my collaborators at the group. And there have been many more that I've not been able to include, but yeah, thank you. So just give me 1 second. Can you still hear me okay?
Yes.
Okay. So just yeah.
So, Mr. Roy, thank you for the presentation. And now let us have questions on anything, really. I would like to have questions of general nature first before the committee, gets together with you alone. So I don't know if there are questions from the room or from others online that are not members, who are not members of the committee. We could start with that, or anybody can ask questions then. I can see this is a very broad topic. You know, you covered a lot in this presentation in a few minutes, and it may be a little intimidating, but you know, I don't know if anybody has any questions here. That would be very welcome.
Yeah, there are more than 30. There are more than 30 people who are online. So go ahead, guys. Anybody online? In the audience?
I'm going to throw a very okay. Anybody? Yeah. I'm going to throw in a little something. I know that several of you here are doing work in personalized medicine. Okay. And I wonder whether you have some comments as to the applicability of some of the conceptual framework that was described here to the field of personalization specifically. So that would be a question for Kaushik, or if someone else wants to pick up this topic, that would may be interesting to follow up and have a little discussion on this.
So in my exploration, I found funded companies, startups today in personalized health. For instance, the one that everyone in the room can look up now is called Glass AI. The claim is that you provide an input and then you provide certain additional criteria and it comes up with a personalized output. But then for me, when I look at that output, and you can do so also on your end, is that there is no apparent way to tell what about that output is correct or not correct. And
Mr. Roy, you're breaking up. Can you try and speak more loudly?
Is it better now? Is it better now?
Yeah, go ahead.
Yeah, okay. So the output from the software in that company's implementation retains the problems that I touched upon in this presentation, which is you don't know what parts of those personalized outputs connect to things that providers would care about. And that is the ultimate goal for personalized health, so that you get a personalized patient profile, sort of a summary dashboard of what they're going through. But if that doesn't connect meaningfully to what the provider wants to see, then you have the same issue. That's what I have found in competitors' works. I'm not sure if anyone else has any experience with this.
Go ahead, Venkat.
I just don't have a question, but I just wanted to say that just in time, that Kaushik is the first author for a recent IEEE article, which is a composite AI with custom compact neurosymbolic models that is just published and from in IEEE. I'm just giving you the link in the chat.
Thank you.
Recording in progress.
So let's turn off microphones here in the room, because we've had with the main computer. It probably didn't see us for a moment. So now we're all back, I think. Thank you. Well, if there are no more questions of a general nature, maybe we can just restrict the meeting to the committee at this point. Any second thoughts on that? No? So everybody please leave, and we'll just have a meeting of the candidate.